Okay, we'll continue with our discussion of the properties of the Fourier transform. We had done two properties earlier. The third property we want to look at is that of time shifting. So the idea is, just to remind, the notation we have been using is we have function gn which has a Fourier transform g of e to the j omega, and we may have a function hn with the Fourier transform h of e to the j omega. Okay. So the time shifting property says that if you have g of n minus n naught, then the Fourier transform of that, so if I just shift my signal in time, let's say you record my voice and then you play it back, you delay it by 10 seconds or 100 seconds. So this is the time delay. In discrete time, that's the samples. Then the Fourier transform of that is just this exponential, complex exponential addition times g of e to the j omega. Okay. Effectively, if you think of it, all that time shift does is add a phase shift to each frequency. So let's try to understand it a little bit more. What does it mean? So let's look at the magnitude and the phase of the Fourier transform of this gn minus n naught separately. Okay. So let's look at first e to the minus j omega n naught, g of e to the j omega. The magnitude of that, now of course the magnitude of that is simply the magnitude of g of e to the j omega, because this does not change anything to the magnitude. So what does it mean that if I shift a signal, if I shift a signal in time, the new frequencies, the frequencies that are present in that signal are exactly the same as in the previous signal. Okay. Which makes intuitive sense because shifting the signal in time doesn't change the rate at which a signal is changing. Okay. So Fourier transform, the frequencies are telling us what are the different speeds at which the signal is changing. And if I just shift it by time, that's not going to change how fast something is wiggling. So because of that, the amount of frequencies that are present in a signal are exactly the same. That's what it means in terms of the phase. In terms of the magnitude, now let's look at the phase. Let's ask what is the phase of g of e to the j omega, e to the minus j omega naught for each little omega. Okay. So what's the phase? Because each frequency has some phase associated with it. What is that phase? Well, that phase is simply phase of g of e to the j omega minus omega naught, omega n naught. So we could have written this as magnitude and phase, right? I can write this as g of e to the j omega, absolute value, e to the j, let's phase of g of e to the j omega. Right? I can always write a complex number in this way, and if I write it this way, then the phase of this whole thing is just because of the phases just add up, this will be the new phase. Okay. In particular, if the phase of the previous signal was 0, if the Fourier transform, the phase of each frequency was 0, then the phases of the new frequencies will be simply, if g of e to the j omega was equal to 0, this means that the phase of frequencies for g of n minus n naught, that is simply equal to minus omega n naught. Okay. So if I plot the magnitude of Fourier transform of g of n minus n naught, that will be exactly equal to the magnitude of the original signal. Okay. And if I plot the phase of the Fourier transform of g of n minus n naught, then that will be equal to minus omega n naught, assuming that the phase of g of n was 0. Okay, and the plot you will get will be, it will be a linear shift, and its slope will be minus n naught. Okay, so that's all a time shift does to the frequencies of the input signal. It just changes the phases of the frequencies. It never changes the magnitude of the frequencies. So if we together use the linearity as well as the time shifting property, it helps us compute the Fourier transform of signals that may be expressed through linear difference equations. Okay, so let's say that we had a difference equation d naught vn plus d1 of vn minus 1, and we say that is equal to some coefficient p naught delta n plus p1 of delta n minus 1. Okay, so first of all, Fourier transform is linear. So if I take the Fourier transform of this whole thing, that is simply equal to the Fourier transform of this on the right hand side, and because of the linearity, I get d naught Fourier transform of Vn plus d1 Fourier transform of V of n minus 1 equal to P naught Fourier transform of delta n plus P1 Fourier transform of delta of n minus 1. So we have now used the linearity property. Let's call the Fourier transform of Vn as V of e to the j omega. Okay. So I'll just write that as d naught V of e to the j omega plus d1. Now this Vn minus 1 is the same as Vn, except that it is shifted by 1 to the right. So this means that if I'm calling the Fourier transform of Vn as V e to the j omega, then the Fourier transform of this, by the time shifting property, that will be equal to e to the minus j omega n naught is 1 here, times V of e to the j omega. Okay. So I get e to the minus j omega V of e to the j omega. Equals, now the Fourier transform of delta, this is one of the things that we had done a few lectures ago. The Fourier transform of delta is, you should think of it as sort of the most fast changing signal, and so it consists of all the frequencies. So the Fourier transform of delta is, so the Fourier transform of delta is 1, so I just get P naught plus P1. Now this is delta of n minus 1. So again, we know the Fourier transform of delta of n, and this is just a shift by 1. So we can use the time shifting property, which means we will get 1 times simply e to the minus j omega n naught, which will be e to the minus j omega. So I get e to the minus j omega. Now I just take V of e to the j omega common. I get d naught plus d1 e to the minus j omega equals p0 plus p1 e to the minus j omega. And now I just take it to the other side. I get v of e to the j omega equals p naught plus p1 e to the minus j omega over d naught plus d1 e to the minus j omega. Okay. It is very similar to what you might have done with computing the z transform when you are given a linear difference equation. The properties are very similar to that. But effectively, linearity and time shifting helps us solve the Fourier transform when we are given equations in terms of difference equations. The fourth property we want to study is that of frequency shifting. It's again a very commonly used property, and it's similar to what you study in the case of continuous time Fourier transform. So the idea is that you define, let's say you are already given Gn, and you multiply your Gn with a complex exponential with frequency omega naught. Okay, so you multiply your Gn with a fixed frequency. This is a frequency of omega is not a variable now. You are given omega naught, which is a fixed value. Okay, so this is complex sinusoid with frequency omega naught. The question is, if you multiply your signal with a complex sinusoid, what happens to the Fourier transform? And the answer is that e to the j omega naught n Gn, its Fourier transform, is the Fourier transform of the original function g shifted by omega naught. Okay. Remember, all that matters in this description is that omega is the variable, so omega minus omega naught means shifting by omega naught. Okay, e to the j is just there to simplify the notation, to make us understand that this corresponds to the discrete time Fourier transform. So let's try to understand the meaning of this. What it says is that the whole Fourier spectrum, okay, Fourier transform of Gn is shifted to the location of the frequency of the sinusoid. So if you this operation this is also called frequency modulation. This is one of the most frequently used operations in, for example, communications. Right? If you are, for example, if you are running a radio station, you are recording some sound, or the sound is at the baseband. The sound is maybe from 0 hertz to 3 hertz. But then FCC tells you that you are allocated a maybe 1030 megahertz location. That's where you need to transmit. Okay. Well, what do you have to do? You have to shift your sound to the location of the frequency which FCC has given you. And this is one of the operations that you do. You can do it in discrete time. It corresponds to the frequency in the continuous time that we'll see later. But effectively, the idea is your frequencies are given around 0, and you want to move them to a certain other location, maybe 1 megahertz or 10 megahertz. How do you do that? You multiply them with a complex exponential, complex sinusoid with the certain frequency. If it's continuous time frequency, then you move them in hertz. If it's discrete time, then you move them between minus pi and pi. So an example will be, let's assume that Gn is such that g of e to the j omega is given by, let's say this is my g of e to the j omega, where it's centered around 0. It goes to some frequency here. Let's say maybe it's pi by 4. Okay. And of course, you have periodicity. So you'll get the same thing everywhere. Okay. And now let's define xn equals e to the j pi n gn, which means you are now multiplying your omega naught, in this case is pi. Right? You can simplify that further. Sometimes you will get it seen as minus 1 to the n. Right? E to the j pi n for n even is 1, and for n odd is minus 1. So you can write it as minus 1 to the n gn. The question is, what does it do to the spectrum? Well, as we saw earlier from this equation, all that is going to happen is that this whole spectrum of your signal will be shifted to where it will now be centered at omega naught, and omega naught in this case is pi. So this whole thing gets shifted. Your new Fourier transform is g of e to the j omega minus pi. Okay. What does that look like? Well, this is your pi. Now you get, this is 0. This whole thing gets shifted here, and this will be pi minus pi by 4 and pi plus pi by 4. Okay. Similarly, you will have a copy here. Minus pi plus pi by 4 and minus pi by 4. Okay. And the same thing will happen. You will have periodic repetition of that. So this operation of modulation is going to just shift your Fourier spectrum, but the shape and the phase and everything else of the new frequencies will stay the same as the previous ones. They will just have a shift. Okay. If something was happening at, let's say, pi by 8, now it will be happening at pi by 8 plus pi, because you shifted things by pi. The next property is that of differentiation in frequency property, which I won't dwell into too much. It really helps in some analysis, but we won't really discuss too much about it. It's very similar to, again, the property that you get in the continuous time. In the continuous time, you must have seen t times g of t. In the discrete time, it is n times g of n. If you take its Fourier transform, the Fourier transform of that is related to the Fourier transform of the original signal with j, and then there is a differentiation e to the j omega with respect to the frequency. So if you want to compute the Fourier transform of n gn, you can simply take the derivative of your original Fourier transform with respect to omega multiplied by j. You get the Fourier transform of the new sequence. The next property is the general modulation property. So The frequency shifting property says if you multiply your signal with a complex sinusoid. This property says if you multiply your signal with another signal, which may or may not be complex sinusoid, what happens? So if I multiply my Gn with Hn, okay, so previously we had Hn equal to this complex sinusoid. Now we are saying it can be anything and it has just a Fourier transform. So the multiplication in time of two signals, now in continuous time you learn that to be equal to, so multiplication in time for continuous time does convolution. In discrete world it's somewhat similar, but because of the fact that the major difference between continuous time and discrete time is we have discrete time Fourier transform is periodic. So we have to account for that periodicity. So it is 1 over 2 pi, and I'll put the limits later. It's g of e to the theta h of e to the j omega minus theta d theta. Right? I keep on saying or keep on reminding you that the variables here are what is next to e to the j. So the variable here is theta, and this is omega minus theta, and you are doing multiplication and you are taking the integration. This looks very much like the convolution operation, except that the limits are minus pi to pi, because of the fact that both G and H are periodic in the frequencies. So this kind of convolution is called periodic convolution. It's again, if I had, for example, two signals G of t convolved with H of t, then the formula for that is minus infinity to infinity g of tau h of t minus tau d tau, right? If you compare these two formulas, what is this saying? That you fix one signal, it's exactly the same. You fix one of the Fourier transforms, you flip the other and shift it by the amount t. It's the same here. You flip it because the variable is now theta. You flip it and then you shift it by the amount omega where you now want to compute. The only difference is that you fix one, you flip the other and slide it, and then you multiply the two signals. But when you are taking the integration, you only care about the integration between minus pi and pi. Okay. And the reason being that the signals that you are now doing are periodic. If you are to actually go minus infinity to infinity, then you will get your answer to be infinity because it just extends everywhere. Right? So that's the only difference between convolution and periodic convolution. It looks very similar, and actually if you explicitly put in Hn equal to what we did for our frequency shifting property, if you put in Hn equal to e to the j omega naught n, then you will get back the frequency shifting property that we derived as part of the fourth property. Okay. The next property, you have seen it in pretty much every transform that you must have done, is that of Parseval's theorem. Intuitively, if you want to think of Parseval's theorem or Parseval's property, the one way of thinking about it is it's just law of conservation of energy in the case of many transforms. Okay, what it in words it says is that energy in one domain, in this case time, equals energy in the other domain. So as we talked about earlier, Fourier transform is just another way of looking at the same signal. But the total energy, if I just look at a signal and I look at it in the frequency domain, the energy that is contained in that signal is not going to change. And that's what Parseval's theorem is saying. It says that if you add up all the entries of your signal absolute value squared, n from minus infinity to infinity, and remember the condition of the Fourier transform, this should be less than infinity, otherwise we cannot compute the Fourier transform. So this is a finite quantity. That energy in time, so this is energy in time. That is equal to the energy. Now the way we will define the energy is over only one period. Okay. If I take the Fourier transform absolute squared and I integrate it, now why don't I have the summation? Because Fourier transform is a continuous function of omega. I get this. These two quantities are equal. Okay. There is a general form of Parseval's theorem which we won't dwell too much. It is actually more general than that, which says that actually if you have two signals, Gn and H conjugate of n, then in frequency that is equal to minus pi to pi multiplication G of e to the j omega H conjugate e to the j omega d omega. How do you derive this special form from the general form? You replace H conjugate n by G conjugate n. Okay? And similarly, you replace H conjugate e to the j omega by G conjugate e to the j omega. And then you use the property that of complex number. What happens if you multiply a complex number with its conjugate? So this is a complex number and this is its conjugate. So if I have a complex number and a conjugate, what is that equal to? So a conjugate is simply equal to absolute value a squared. Okay, and you can verify that by doing explicit multiplication. So that's how you get this special form from the general form. Okay, but for most purposes, you should just focus on the special form, which is saying energy in time equals energy in frequency. So now we come to the most important property, which will help us understand the role of discrete time LTI systems in terms of frequencies. We already know what discrete time LTI systems do in time. They do convolution, but understanding that role is a little difficult. So in frequencies, what does that do? For that, we need the convolution property. The convolution property says that if I have two time domain signals and I convolve them in discrete time and I take their Fourier transform, that is equivalent to multiplying their respective discrete time Fourier transforms. This convolution property is exactly the same as in continuous time. The reverse of that is a little different. If you multiply two signals in time, in discrete time, you get periodic convolution. In continuous time, you get plane convolution. But the forward of that is the same for both. If you convolve two time domain signals, you always get their multiplication of the Fourier transforms. Okay. I won't go into the proof, but what the convolution property does is it helps us understand the actions of a discrete time LTI system in terms of frequencies. Okay. So remember, a discrete time LTI system is only described, the only thing you need to know to understand a discrete time LTI system is its impulse response. If you know its impulse response, then the output is simply equal to convolution of the input and the impulse response. So now you could ask, if xn has certain amount of frequencies, and of course yn has certain amount of frequencies, what are the frequencies of yn in relation to xn? So if you want to compute that, you just take the Fourier transform of yn, which is Fourier transform of xn convolved with hn, okay? But according to what we just saw earlier, the property, convolution property, that is equal to Fourier transform of xn multiplied with Fourier transform of hn. So the Fourier transform of xn, let's call that x of e to the j omega. Fourier transform of hn, let's call that h of e to the j omega. And Fourier transform of yn, call it y of e to the j omega. So what it says is that the frequencies of your output signal are simply given by the multiplication of the complex value associated with your frequency of the input signal times the frequencies associated with the impulse response. So this h of e to the j omega, because of this reason, it's called frequency response. Okay. So let's try to break it down in terms of magnitude and phase. So y of e to the j omega, I can write that as absolute value of y e to the j omega times e to the j theta of omega, where theta of omega is the phase associated with this complex number. So this is a complex number for each little omega, which means this complex number has a magnitude and a phase. Okay. Similarly, x of e to the j omega is magnitude and phase, and I'll call that phase of x of e to the j omega. H of e to the j omega has magnitude and phase. So now, based upon this expression, let's ask ourselves what happens to the magnitude of the output frequencies and the phases of the output frequencies. And it's similar to the 3 or 4 cases that we had done for the continuous time earlier in the class. So number 1 case is that if x of e to the j omega is equal to 0 for some frequency omega, say omega equals to pi by 4, for example. Okay. So if my input frequency is 0 for certain frequency, what is my output frequency? Well, I'm multiplying the output frequency equals to input frequency magnitude times frequency response. No matter what the frequency response is, since I'm multiplying with 0, I get the output frequency y of e to the j omega equal to 0. Okay. So this means that if the input signal has no frequency at certain values of omega, then output signal cannot have those frequencies either. That's one of the most basic principles that discrete time LTI systems or continuous time LTI systems cannot add frequencies to the input signals. The other part is that if h of e to the j omega equals to 0 for some frequency, so the relationship is, again, you are multiplying two numbers and one of the numbers is 0. Well, it doesn't matter what the input frequency was, how much of the input frequency was present at that value. If your frequency response for that frequency value is 0, then your output is simply 0. So y of e to the j omega equals to 0 for that So in other words, you can use the discrete time LTI systems to kill some of the frequencies in your input signal. Now, if both of your X and H are not 0, then we have to talk about the magnitudes and the phases. If both the input don't have the 0 frequencies for those, and the frequency response is not 0, then the output, we have to talk about what are the magnitudes of the output frequencies and what are the phases of the output frequencies. Okay. So for that, we'll split our answer into, we'll look at first the amplitude or magnitude of output frequencies. And if you are multiplying two complex numbers, their magnitudes simply get multiplied. So the magnitude of the output frequencies will be equal to x of e to the j omega absolute value times h of e to the j omega absolute value. In other words, if you want to scale up some of the frequencies or scale down some of the frequencies, you can design your LTI system such that its frequency response is at the right value. So let's say that your x of e to the j omega, its magnitude was like this, from minus pi by 4 to pi by 4. And what you wanted was that between minus pi by 8, so all of this, the height of this is 1, and what you wanted was that between minus pi by 8 and pi by 8, you want to reduce the magnitude down to 1/2. Okay? So what you can do is design an h of e to the j omega, which you could say, I don't care what the other frequencies do, I'll just keep all the frequencies 1, but between minus pi by 8 and pi by 8, so this is minus pi by 8 and pi by 8. This is height 1 and this is height 1/2. Okay, and now you are simply going to multiply these two together to compute y of e to the j omega, the magnitude. Okay. That will exactly be, well, this is all getting multiplied by 1, so I get back the same thing between minus pi by 4 and pi by 4. This is pi by 4. But between minus pi by 8 and minus pi by 8, I now reduce the amount of these frequencies to 1/2. Okay. At some level, you can think of it that I have reduced the contribution of low frequencies using this operation, the operation that I've just done. Similarly, you can change any other frequencies that you like by designing an appropriate frequency response magnitude. Okay. Now, for complex numbers, magnitude is not the only thing. We also have to think about the phase. So the phase of y of e to the j omega, you multiply two complex numbers, you're looking at their magnitude, it's equal to the multiplication of the respective magnitudes of the numbers. You're looking at the phases, the phase of the multiplication is equal to, so you just add the phase of x of e to the j omega plus the phase of h of e to the j omega. Okay. So the phases of the frequencies get changed by the amount that the phase of h of e to the j omega exists at that value. So if both the phases were 0, then actually the new phase will be 0. If x phase was 0 but h had a certain phase, you just inherit that phase because it's just additive. So discrete time, because of this convolution property, we are able to interpret the operations that a discrete time LTI system does in terms of frequencies. Number one, a discrete time LTI system can be used to remove frequencies in your input signal. Number two, it can be used to increase or decrease the magnitude of some of the frequencies in your input signal. And number three, it can be used to change the phases of the frequencies in your input signal. It cannot be used to add new frequencies to the input signal. So based upon that, let's look at an example, which is simply that the impulse response of an LTI system is Hn equals delta of n minus 10. This impulse response says that if you input an impulse, your output gets shifted by 10 samples. Okay. You can compute that using convolution, and I did the same in the quiz if you want to look at it, but what it does is if you convolve your signal with an impulse, all that happens is your signal gets shifted to the location of the impulse. So you can compute that and it will end up being x of n minus 10. Okay. Now, if you want to look at it in terms of frequency domain, what we know is that y of e to the j omega equals x of e to the j omega times h of e to the j omega. So what is the Fourier transform of Hn? That's the time shifting property that we did earlier. It's e to the minus j omega n naught, and n naught in this case is 10. So e to the minus j 10 omega, and delta's Fourier transform is 1, so that's just 1. Okay. So what we get is x of e to the j omega times e to the minus j 10 omega. If I now compute the magnitude of this, I get back x of e to the j omega, magnitude of e to the minus 10 omega. The magnitude of a complex sinusoid is just 1, so that is x of e to the j omega. This means that if my LTI system's impulse response is simply a shift in time, then it does not do anything to the magnitude of my frequencies. If a frequency has a certain magnitude, at the output I will have the same magnitude. And this makes again intuitive sense because all the system is doing is it is delaying the input. If I delay the input, I cannot change the rate at which the signal is wiggling. On the other hand, if I compute the angle, the phase associated with the Fourier transform, I get phase of x of e to the j omega minus 10 omega. Okay. So if my phase originally was, let's say, 0, then I get only minus 10 omega. Oftentimes, if you look at this, what this is saying is that if your Fourier transform of your impulse response corresponding to a time shift, if it's just doing the time shift, then the effect of that in the output frequencies is that it is going to add a linear phase shift to your output frequencies. This is linear, so this is a linear function of omega. The power of this is 1. It's a linear function. So all that says is that each of the frequencies gets shifted in proportion, get a phase shift in proportional to their value. If it's a smaller frequency, it gets a smaller phase shift. If it's a larger frequency, it gets a larger phase shift. Okay? And oftentimes what we say because of this reason, we say that time shifting alone is not that big a deal. Or alternatively, if we sometimes look at the Fourier transform, then we say that our Fourier transform has this kind of a linear relationship in phase. We say that that's not a big deal because linear phase shift is equal to simply time shift. And if I shift something in time, it doesn't change the nature of the signal. Okay. Again, the analogy that if you hear me, what I'm saying today, or if you hear the same recording 10 days later, it's not going to change the amount of information that you get. So we'll repeat that many times, that a linear phase shift does not change anything in terms of information, and we are happy if we get only linear phase shift from our LTI system. Another example that I want to discuss is that of the notion of an inverse system. So many times what happens is that an LTI system actually corresponds to something that happens in nature. For example, if I am in a big hall and I'm speaking, there's going to be echoes from the hall, right? And the echoes can be modeled, the operation of echoes, the effect of the hall on my voice input can be modeled as an LTI system. We won't go into that. But what happens is in discrete time, if you model that, this Hn can be, you have an Xn, you get Yn, and this Hn can be given by nature. Okay? So someone modeled whatever nature is doing to your input signal through an LTI system. And then the goal in engineering could be to design an inverse system to cancel out the effects of that natural phenomenon. So what you could be doing, for example, is if you are designing a recording system for, let's say, music industry, and someone is playing in a hall where there's a lot of echo, what you want to do is, before you record that, you want to process it so that the effects of that echo are canceled. That's called designing an inverse system, and you can, not always, but sometimes you can design it as another LTI system. So the goal is you design, so this is given by nature, Hn, and this is, you need to design Gn such that you get something called X tilde n, which is approximately equal to Xn. Okay. Now, doing this design operation, looking at just the time domain operation is really hard. So if you think of it, each of these LTI systems corresponds to convolution. So we can figure out what is X tilde of n. X tilde of n is Yn convolved with Gn. Okay. But what is Yn? Yn is Xn convolved with Hn. Since convolution doesn't care which way you do it, we can remove these parentheses and we can simply write as Xn Hn and Gn. And what we want is that all of this is approximately equal to Xn. Now this is convolution, not multiplication. So while you may want to just say, well, let's write, if you want to compute Gn, let's write Gn equal to Xn divided by Xn convolved with Hn, it doesn't make sense. Okay? You can move things around in multiplication, but this is convolution. So a better operation is you write this in the form of frequencies. So you say, let's write down the Fourier transform of x tilde of n equal to Fourier transform of xn, hn, and gn. Now you want this Fourier transform, if you want your signal to be xn, then you want the Fourier transform to be the Fourier transform of x of e to the j omega. And by the convolution property, you can simply write these as multiplications. So the Fourier transform of x times the Fourier transform of h times the Fourier transform of g. Okay? Now these are multiplication and you can do the divisions. So your design goal is design Gn such that g of e to the j omega, h of e to the j omega equals 1. Now we have to be careful. I want to ideally write g of e to the j omega equals 1 over h of e to the j omega. But what do I have to be careful about? So assuming that h of e to the j omega is not equal to 0 for every little omega. Okay, it's not enough to have it for some omega. For every little omega, it must not be equal to 0. If that is the case, then you can write g of e to the j omega equal to 1 over h of e to the j omega, or h of e to the j omega inverse. So assuming h of e to the j omega is not equal to 0 for every omega. Okay? So now we know if you want to design an inverse system, if we know what nature does to the frequencies, we can simply take the inverse of that, and then we can take the inverse Fourier transform of that. So our Gn will be defined as Fourier transform inverse of h of e to the j omega inverse. Okay? This is no, there are some more technicalities involved in doing this because oftentimes what you also get is noise in the system, so you can't always do it. But this is sort of one of the most fundamental operations that LTI systems are used for, to cancel the effects of something that nature does. Okay? Even if you do this transmission on your cell phones, when you transmit these radio frequencies over your cell phones, they bounce around different buildings before they reach the cell phone tower. And one of the first things that the cell phone tower ends up doing is nullifying the effects of those bounces so that you can really figure out what was transmitted. So inverse systems, design of those, or canceling the effects of what nature does is a very, very important concept in signal processing. Another application that you can think of it, which is not time domain signal, is effectively canceling the blurring of pictures. Okay? If you use a camera and your hand shakes and it gets a little blurred, you can design software that can try to eliminate some of the effects of that blur. Again, that's called an inverse problem. Okay? So from here on out, we need to remember that all the information in LTI systems is captured either in the impulse response, or we can also talk about its frequency response. frequency response can be written as, since it's a complex number for every frequency, its magnitude times e to the j phase of that. Okay. So this is called the magnitude response of your filter of your system. This is called the phase response. And oftentimes the magnitude response will be displayed in dBs, so you will often actually be plotting 10 log 10 of absolute value of h of e to the j omega. Okay. I want to finish this discussion with one last example, which is that of a moving average filter. This moving average filter, actually, if you ever were to go into finance, you will hear it day in and day out. It's used in stock analysis all the time. People talk about 10-day moving average, 50-day moving average, 200-day moving average, right? And many stock analysts will use that as benchmarks for whether you should sell the stock now or buy the stock. But what is this moving average really doing? Let's try to look at that. So mathematically, the moving average filter is simply, it takes a discrete time signal, generates output, and if you have an m-point moving average filter, then that corresponds to, the output is simply equal to, the idea is you take your current input and the last m-1 inputs and you average them. That's all moving average filter does. Okay. It does L equal to 0 to m-1 x of n minus L. Now, if you remember the first part of your quiz, this is a linear filter because it does not have any powers other than linear powers. This is a linear system, and it's a time invariant system because none of its coefficients are changing with time. Its coefficients are only 1 over m. Okay? So this filter, all it does is take the current value. Let's go back to the stock analogy. If you are computing the 20-day moving average, you take today's value of a stock and the last 19 days, you add them all up and you divide them by 20. Okay? That's the moving average filter. And what is the impulse response of that? Well, you replace x by delta. That's the definition of the impulse response. You replace your input with delta function. So in that case, your Hn ends up being 1 over m summation L equal to 0 to m minus 1 delta of n minus L. Okay? Your impulse response simply looks like it has m1s and 0 everywhere else. Okay? It's equal to 1 over m for 0 less than or equal to n less than or equal to m minus 1 and 0 otherwise. Okay? So for 200-day moving average, m will be equal to 200. For 50-day, capital M will be equal to 50. Now, if you want to understand what is this filter really doing, then what we have to do is compute its Fourier transform so that we can look at the frequency response of this filter. So let's compute the frequency response, and all we have to do is use our linearity and the frequency and the time shifting property. Okay, So we get 1 over m summation L equal to 0 to m minus 1 Fourier transform of delta of n minus L because of the linearity. We have now done it many times. It's a shift of delta, so it will be simply e to the minus j omega n naught, and n naught in this case is L. So it is simply 1 over m summation L equal to 0 to m minus 1 e to the minus j omega L. So these values should be 1 over m. Okay, going back to the Fourier transform, now this is a geometric sum. Okay, and you just hand it in the homework in which you must have solved that using the geometric sum formula, which is if you are given summation of r to the n equal to 0 to n minus 1, that is simply 1 minus r over n over 1 minus r. If I use that, I get 1 over m 1 minus e to the minus j m omega over 1 minus e to the minus j omega. Okay. Now, you can simplify it further using the Euler's identity. Apply the Euler's identity on the numerator and the denominator, and you get sine of m omega by 2 over sine of omega by 2 times e to the minus j m plus 1 omega by 2. Okay. Now, I'm really interested in understanding what is happening in the magnitude of this moving average filter. If I do that, that is simply equal to 1 over m, absolute value of sine of omega m by 2 over sine of omega by 2. You will see this expression many times. You should think of it as a discrete time equivalent of sinc. Okay, this is not sinc itself. Why it can't be a sinc? Because remember, sinc is not periodic, and the Fourier transform is always periodic in little omega. But between minus pi and pi, this function behaves very much like a sinc. Between minus pi and pi, it behaves like a sinc, and then it goes back to repeating itself. Okay, so this is the Fourier transform. You can also plot the phase of this, which is a little bit more complicated because of the way that the signs of these things interact. This part of the phase is easy. But let's look at the plot of this, the magnitude response of this filter, of this moving average filter, and try to understand what is this filter doing. So this is the plot of the magnitude response. I'll focus on the magnitude response. It is showing you the filter for two values, m equal to 5, m equal to 14. Let's look at what is happening for m equals to 14. Okay, it is basically preserving most of these frequencies, but then it's damping the frequencies. So the height of this is 1. It's damping all of these other frequencies. Now this is omega over pi, okay, on the x-axis. So you should really think of it, this is going up to pi. Okay, so this thing is up to point maybe 1/8 pi. It is keeping some of the frequencies, but it's making the other frequencies contribution really, really small. Now, if you make the contribution of high frequencies small, what does that do to your input signal? High frequencies mean your signal is wiggling fast. Right? High frequencies mean your signal is wiggling fast. If I remove those high frequencies from your input signal, what happens? My signal will start to wiggle now slowly. Okay, it can't change that fast. This red curve is for m equal to 5. As I reduce my moving average, So instead of going back, let's say 14 days, I go back only 5 days. What happens? I am now keeping more of my frequencies. My frequency response has really widened. Okay, it has widened to this range. It's now going up to perhaps like 0.38 pi. So I am now keeping more of my frequencies, which means that I'm not throwing away that much wiggling of my signal. Okay, so if you had to intuitively ask about what is the moving average filter doing, what it is doing is it is smoothing out the variations of your input signal. And that's why stock market people love it, because stocks in general are wiggling at a very fast rate. And it's hard for you to really determine what is in general the stock doing on a broader scale. So what I did here was plot the moving average for Apple of a 10-day moving average, a 50-day moving average, and a 200-day moving average. This is accurate. This is real Apple stock data on February 5th, 2014. Okay. Now, this really wiggly curve, and it looks like a continuous curve because I just plotted it that way. It's really discrete data. Every day you have a discrete value, right? Stock data is a discrete signal. So this really wiggly green curve is the real stock data. And it has a lot of high frequencies because it's wiggling really fast, because stocks fluctuate at a very high rate. If I take a 10-day moving average, that's effectively throwing away some of the high frequencies. That's going to reduce the amount of wiggling in my data. And you get this curve, which is hard to see because this is a green curve. This is 10-day moving average. Okay. And it's almost lying on top of that, but it doesn't have that many strong wiggles. But now I increase the value of my M. Remember, then the more I make my M, if you look at this plot, the more higher frequencies I'm throwing away. Okay. So I increase my M to 50, and I get back this is 50-day moving average. Okay. And now you see that the fluctuations have really slowed down. My whole signal is now slowly varying. And you could use that as an indication of whether my stock is, for example, going up or down, right? I'm not trying to give an advice on how to pick stocks. I'm just trying to give you a sense of what this filter is doing. Because really what people in the stock market are calling moving average is nothing but a discrete time LTI system. If I now increase my moving average to 200, this means that I am now throwing even more of my frequencies away and keeping very small amount of low frequencies. And low frequency means that my signal has to wiggle at a very slow rate. And because of that, this 2-day moving average you see is very smooth. It is in general following the trend of my stock movement, but at a very slow pace. Okay, my stock here, if you look at here, my moving average is still going up, even though my stock value has now started to go down. Okay, so this is a real world example of what an abstract moving average filter magnitude response, what is it doing? It can help you understand. If you want to smooth out signals, you want to design filters which keep low frequencies and throw away high frequencies. And moving average filter is one of the simplest filters that you can design. You can come up with more sophisticated filters which do the same job, maybe better job, but they may be hard to explain to some of the stock market people. But that's all this moving average filter is doing.